Welcome. I'm Mark Reynolds, and with this video, we begin Math 441 Real Analysis at Shippensburg University. This course uses the book Understanding Analysis by Stephen Abbott, and this is a fantastic book. I really like it a lot. So in this lecture and the other ones, I really do follow this book pretty closely. So maybe I'd recommend having it by your side as you watch these lectures. Abbott writes, "This one-semester course exposes students to the rich rewards inherent in taking a mathematically rigorous approach to the study of functions of a real variable. The aim of a course in real analysis should be to challenge and improve mathematical intuition rather than to verify it. My intent is to bring an intellectual liveliness to this course by offering the beginning student access to some truly significant achievements of the subject." There are two themes you're going to see again and again in this course. The first one is approximation, and the second is the transition from the finite to the infinite. And I think that's absolutely fascinating. We really will see that theme again and again. So just kind of keep an eye out for those two things as we go throughout the semester. In Chapter 1, this video will cover sections 1.1 and 1.2. The first section in every chapter is a discussion. It sort of lays the groundwork and inspires what's to follow for the rest of the chapter. So in this particular case, we take a look at the square root of 2. And then in 1.2, we'll look at some preliminaries for real analysis, things like sets, functions, logic and proof, and induction. Okay, let's get started. So 1.1 begins talking about the square root of 2. So here's our theorem 1.1.1. There is no rational number whose square is 2. Why is that? Well, here's a proof. This was known to the ancient Greeks, and more or less, here's kind of how they figured it out. If the square root of 2 is rational, so this is a proof by contradiction, then you could write it as a over b, where a and b are integers. Multiply both sides by b, square both sides, and we get 2b squared equals a squared. And now, and now what? At this point, there are many different directions you can go, and there are many different proofs that the square root of 2 is irrational. But here's one way that we might approach it. That equality, that contradicts uniqueness of prime factorization. How exactly? Do you see that? So, uniqueness of prime factorization says every integer can be expressed as a product of primes in only one way. So this equality means I have the same number on both sides. It's just represented in two different ways. Now, if I have an integer a, then a has a prime factorization, and it has maybe a certain number of 2's in that prime factorization. So if I square it, every prime will appear twice. Or if a prime appears, say, 3 times in a, then when I square it, the prime will appear 6 times. So in a squared, every prime appears an even number of times. Similarly, with b squared, every prime in the prime factorization of b appears an even number of times in the prime factorization of b squared. Now focus on the number 2. On the left-hand side of this equation, how many times does 2 appear as a factor? It must appear an odd number of times. But on the right, 2 appears an even number of times, maybe 0 times, but that's okay also. And there's our contradiction. The number 2 appears an odd number of times on the left and an even number of times on the right. And so this is impossible. I cannot write the square root of 2 as a fraction of 2 integers. The upshot of this is that the rational numbers aren't all the numbers. Natural numbers can be written this way. It's the set denoted with a double struck n, 1, 2, 3, 4, and so on. The integers denoted with a double struck z. It's all the natural numbers, the positives, and the negatives of the natural numbers, and also 0. We have rational numbers, which is the set of all fractions of integers, a and b, such that the denominator is not 0. And then the real numbers, this is a little more vague. In a sense, it's all numbers. But what does that really mean? Starting with the naturals, I can construct the integers. And then once I have the integers, I use those to construct the rationals. But how do I go from the rationals to the reals? That's a little strange. Abbott writes, the question of how to actually construct the real numbers from the rational numbers is rather complicated business. The reals fills in the gaps of the rationals, and in fact, much of chapter 1 will be spent really trying to understand this more fully. Let's talk about sets. I can write something like this. This notation means X is an element of A union B. The fact that I'm doing a union implies that A and B, those are sets, and that means that X is in set A or set B. We can write X is an element of A intersect B, and that means that X is in A and B. For union, as Venn diagrams, I think of the union as shading in everything. And for intersection, I think of it as shading in just whatever they have in common. These are the elements that are in both A and B. Set builder notation is a great way to describe sets. We read this as set S is the set of all rational numbers R, is the set of all R that are in my set of rational numbers, such that R squared is less than 2. Take a second, pause the video if you need to, and really get in your mind, what does that set look like? Where do those numbers live on the real number line? Maybe something like this. So I'm going to shade in the real number line, all the things between negative square root of 2 and positive square root of 2, not including them. But also I want to be careful because I'm not really shading in all the numbers between negative square root of 2 and positive square root of 2. I'm only shading in the rational numbers. So lots and lots and lots and lots of little dots. Basically, it looks like a line, but it's only the rational numbers strictly between the negative the square root of 2 and positive the square root of 2. If A intersect B is nothing, that is the null set or it's the empty set, then A and B are disjoint. It's this kind of a situation here. Sets A and B have nothing in common. We call them disjoint. When I write A equals B as sets, that means that set A is contained in set B and set B is contained in set A. This is often how we prove equality of the sets. We prove that set A is contained in set B, and we prove that B is contained in A. If I can show both of those containments, then I know that the two sets are in fact equal. The union and intersection of an infinite collection of sets. Now this is a little more interesting. I like this. We will see this quite a bit in this course. So imagine we have a bunch of sets. In fact, we have infinitely many sets. Set A1, A2, A3, and so on. Set A1 is the set of all natural numbers 1 and greater. Set A2 is the set of all natural numbers 2 and greater. Set A3 is the set of all natural numbers 3 and greater, and so on. Can you get a sense of what A sub n looks like? And is there any kind of nesting taking place? Pause the video again, make sure you have a good sense of this, and then continue on when you're ready. You might observe A sub 1 is a superset of A sub 2. And in fact, A sub n is a superset of A sub n plus 1. Even more generally, see if you believe this, A sub n is a superset of A sub m whenever n is less than m. So it's these kind of relationships that are important to understand and wrestle with and make sure that you see them. So let me ask, what if I were to take the union, this infinite union as little n goes from 1 to infinity of A sub n? That's basically the union of all these sets. What would you get? Here's another way of writing that same thing, just with different notation. I like this. We write n is an element of the natural numbers. I'm taking the union of that of A sub n. What do we get? Write down an answer. Write it down before I tell you what the answer is. Commit to it. See what you think. All right, I'll tell you the answer in a second. Let me move on for right now, because I just want to also mention intersection. What about the intersection of all of those sets? If I take A1 intersect A2, intersect A3, intersect A4, forever and ever and ever, what do you get? All right, Have you committed both of your answers? If not, pause the video, write down your answers. Otherwise, here we go. I'll tell you what it is. For union, when I take the union of all these sets, what we get is the set of all natural numbers. In fact, A1 is the set of natural numbers, and everything after A1 is contained in A1. So by taking the union of all of those, I'll never get anything bigger than A1 itself, and so that's what we end up with. Now, the infinite intersection ends up with nothing. There is no number in that set. Consider the number 5. Is the number 5 in the intersection? Well, 5 is in the first few sets, but once I get to A sub 6, then 5 is no longer in A sub 6, and so 5 is not in the infinite intersection. In fact, any number, 1,000,000. 1,000,000 is not in this intersection, because eventually I'm going to get to set A sub 1,000,001, and that does not contain the number 1,000,000. And so any number you pick eventually is not in these sets. And so the infinite intersection contains nothing. It's good to remember some laws about set complement. If I have an intersection, A intersect B, and I take the complement of that, that's the same thing as taking A complement union B complement. And if I have the union of two sets, A union B, and I take the complement of that, the result is the same as A complement intersect B complement. It's kind of curious how the intersection turns into a union when I take the complement individually, and a union turns into an intersection when we take the complement individually. These are called De Morgan's laws. Let's discuss functions. Here's our definition. Given two sets, A and B, a function from A to B is a rule or mapping that takes each element of A and associates with it a single element of B. So here's a set A with 4 elements, and here's a set B with 4 elements, and maybe my function maps the first element to there, and it maps the second guy again to the first, and the third guy again to the first, and I don't know, maybe something like that. So maybe this is a function f that maps A to B. Okay? We write f colon A arrow B to mean that f is a function that takes elements of A and maps them onto elements in B. F of x represents the element in B associated with x by the function f. So, for example, if x is that element on the bottom of A, and if f is the function that does the mapping, then this element of B is f of x. A is the domain of the function, B is the codomain. The domain of the function is the set of all elements that get mapped onto something. Right? So it's important to see what I'm getting at here is that every element in A is the tail of an arrow. Nothing in A is omitted. Everything in A gets mapped somewhere. Now, what is the range of my function? Do you know what that is? How would you write the range as a set? Here's one way. So sometimes you might see RNG, range of F. It's the set of all. How about f of x, such that x is an element of A? That's one way we might represent the range. The Dirichlet function. This is a nice example of a function because the definition of a function is pretty broad. Really weird things can be functions. And the Dirichlet function is kind of weird. It makes a nice example that we will refer to again many times in the future. So g of x is 1 if x is rational and 0 if x is irrational. How would you graph that thing? So here's my height 1. Every time I have a rational value of x, I'm going to plot a point that's a value of 1. So 1/2, 1/3, all the fractions. Every time I have a fractional value, a rational number on the bottom, it gets plotted with a height of 1. And of course, there are so many rational numbers that even though it's a bunch of dots, eventually it kind of looks like a line. But the function has a value of 0 if the input is irrational. So anytime there's an irrational number, we get a value of 0 that's being plotted. And again, there are so many dots that eventually it starts to look like a line. So we have a set of dots for every irrational number and a set of dots for all the rational numbers. Very strange, very discontinuous. It sort of stretches what we think of what a function can do. The triangle inequalities come up again and again in this course. Here's your basic triangle inequality. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And this is very easily proven just by considering positive and negative values of a and b and seeing the relationships with each other. But there's a really nice corollary, and maybe on your own you can think about how would you prove that corollary if you believe the triangle inequality up above. And that's the absolute value of a minus b less than or equal to absolute value of a minus c plus the absolute value of c minus b. Here's what's important. Whenever you see a difference in absolute value, think of it. Think as 2 points on the number line, a and b, and that absolute value is telling us the distance between a and b on the number line. Okay, whenever you see two values as a difference in absolute value, that is the distance between those two numbers on the real number line. And so we're saying that the distance between a and b is less than or equal to the distance from a to c, so maybe c is out here, plus the distance from c to b. And that's actually believable on the picture. And it's also believable that if c is outside of a and b, then we actually have a strict inequality. And if c is some value inside, then we actually have an equality. But in either case, absolute value of a minus b is less than or equal to absolute value of a minus c plus absolute value of c minus b. And Abbott says this is fantastically important. Another corollary that he does not explicitly state in the book, but it comes up in a few homework problems, is what we might call the reverse triangle inequality. So I'll just leave it right there, and we can talk about that a little bit more in class. But we'll see this every once in a while. Maybe, like I said, on your own, it might be a good exercise believing the first step if you can prove the two corollaries. Let us talk about logic and proof. Here's what Abbott writes. Writing rigorous mathematical proofs is a skill best learned by doing, and there is plenty of on-the-job training just ahead. As Hardy indicates, there is an artistic quality to mathematics of this type, which may or may not come easily, but that is not to say that anything especially mysterious is happening. A proof is an essay of sorts. It is a set of carefully crafted directions which, when followed, should leave the reader absolutely convinced of the truth of the proposition in question. To achieve this, the steps in a proof must follow logically from previous steps or be justified by some other agreed-upon set of facts. In addition to being valid, these steps must also fit coherently together to form a cogent argument. Mathematics has a specialized vocabulary, to be sure, but that does not exempt a good proof from being written in grammatically correct English. A proof is not just a string of symbols together. Put some English words in there, guide the reader along, explain what's happening. Perhaps as an example, let's take a look at theorem 1.2.6, and we'll think about the proof for this. Two real numbers, a and b, are equal if and only if, for every real number epsilon greater than 0, it follows that the absolute value of a minus b is less than epsilon. Pause the video, read this through a few times, get it firmly in your head, see what it's really saying. And then when you're ready to keep on going, we'll do the proof. All right, here it is. Why is this true? Well, first of all, this statement is an if and only if statement. So there's really two different things we have to prove. We have to prove that if two real numbers a and b are equal, then for every real number epsilon greater than 0, it follows that absolute value a minus b is less than epsilon. That's the first part of the proof. And then for the second part of the proof, I make this my hypothesis. If for every real number epsilon greater than 0, it follows that absolute value a minus b is less than epsilon. If that's true, then two real numbers a and b are equal. Okay, So we have two mini proofs to go through. Mini proof number one. Let's suppose that A and B are equal. My hypothesis is the first part of the proposition, and I want to prove the second. If A and B are equal, then the absolute value of A minus B is the absolute value of 0. A and B are equal, so A minus B equals 0, and so that's 0. Thus, for every epsilon greater than 0, so epsilon is a positive number, it follows that the absolute value of A minus B is less than epsilon. Indeed, 0 is less than any positive number. Let's go in the other direction. Let's suppose that for all epsilon greater than 0, we have the absolute value of A minus B is less than epsilon. So I'm assuming the second part, and I want to prove the first. What do I want to prove? I want to prove that A and B are equal. So I might put a little thought bubble on this second part. Where I'm going is I want to prove A equals B, given this hypothesis. So we'll proceed by contradiction. Let's assume that A is not equal to B and just see what happens. Well, if A is not B, I can let epsilon sub 0, say epsilon naught, let that be the absolute value of A minus B. So in my picture here, I have a real number line. Here's A, and there's B. And I'm assuming that they're not actually the same thing. So there really is some distance between that. Distance there, and that distance between A and B, that is my epsilon naught. Well, since A is not equal to B, epsilon naught really is greater than 0. Okay, we believe it. Now the hypothesis says then that my absolute value of A minus B must be less than epsilon naught. Because look back at the hypothesis. For all epsilon greater than 0, we have A minus absolute value A minus B is less than epsilon. So in particular, epsilon naught is greater than 0. So my hypothesis tells me absolute value A minus B must be less than epsilon naught. But this is ridiculous, right? Because what is epsilon naught actually? Epsilon naught is the absolute value of A minus B. But absolute value of A minus B is epsilon naught. I can't have absolute value of A minus B strictly less than the absolute value of A minus B. There's our contradiction. When I reach a contradiction in a proof, I think to myself, oh, I must have made a mistake. I must have made a bad assumption. So you bubble up backwards through the proof looking for where you made a mistake or an assumption, and there it is. We assumed that A was not equal to B. That was just an assumption without any foundation at all. I reached a contradiction, therefore I know that assumption must be wrong. In fact, it must be the case A equals B. And that completes the proof. Let's talk about induction as a proof technique. Here's a nice example that makes use of induction. So let's say we have a sequence of numbers, x1, x2, x3, and so on, and this sequence is defined recursively as an initial condition, x1 is 1, and then for the recursive definition, we say that x sub n plus 1 is 1/2 xn plus 1. So any term in this sequence is half the previous term plus 1. We can calculate out the first few terms. So x1 is 1, x2 is half of that plus 1, which is 3/2. x3 is half of 3/2 plus 1, which is 7/4, and so on. Now it looks like these numbers are increasing. Will this sequence always increase forever and ever and ever? So there's our claim. We claim that x sub n is less than or equal to x sub n plus 1 for all n in my set of natural numbers. So we'll prove this by induction. Now the first part is the base case. I have to establish that it actually begins that way. Is x sub 1 less than or equal to x sub 2? And yes, we calculated them out. 1 really is less than or equal to 3/2, and so the base case is complete. Now we make our induction hypothesis. Let's assume that x sub n is less than or equal to x sub n plus 1 for some n. And what do I want to show? So again, here's where I put my thought bubbles whenever I'm thinking ahead. think, where am I going with this? What do I want to show? I've assumed that xn is less than or equal to x sub n plus 1, and I want to show the next step. I want to prove that x sub n plus 1 is less than or equal to x sub n plus 2. So can we do that? There are several ways you might approach this. Here's one way. Multiply both sides by a half and add 1. So on the left-hand side, I get 1/2 xn plus 1. On the right-hand side, 1/2 xn plus 1 plus 1. And the multiplying by half and the adding 1, that doesn't affect the inequality. So I still have the same inequality in there. And what do you notice about that expression on the left? That is exactly x sub n plus 1. And this expression on the right, that is exactly x sub n plus 2. And there, we did it. Our induction is complete. So very briefly, I wrote done. More formally, we might write, thus by induction, the claim is proved. All right, that does it for the induction proof, and that does it for this video. I look forward to seeing you in class, and we will discuss any questions you have from this, and we'll also talk about the homework for this section. All right, take care. I'll see you soon.